Let's look at a couple of simulations to investigate how this Eckhaus instability really looks. I mean, we know, okay, we've now figured out that there's a perturbation in the wave number modulation. So it's modulated and they're slightly compressed and slightly expanded. And depending on that diffusion coefficient, which depends on the wave number, these perturbations either decay or they grow. And in particular, we want to see what happens when they grow, right? When they decay, well, we know already what happens. We saw that in earlier simulations, and it will just go to a periodic pattern. Okay, so let's do that with some simulations. Let's use the Swift-Hornburg model that we used before. And we know that near onset, it will be described by the Ginzburg-Lendau equation. So these results definitely have to apply, even quantitatively and qualitatively at least, or even further above onset. So, okay, so let's generate a pattern. So for some value of mu, we just have a pattern. This has now 12 wavelengths in the box. And so now we make a perturbation. And we showed that the Eckhaus instability is a long wave instability. And so let's make a perturbation that modulates the wave number, the pattern, over a long wavelength, as in the whole system. So here you see the perturbation. You can't really see the distinction between the lines, but you see here there's only red and here's also some blue. And that's because here the pattern is slightly shifted to the right, whereas here it's slightly shifted to the left, and it's not shifted here. So there's some compression and some expansion that's barely visible, but it's a perturbation, and we want to see what happens. Okay, so I just have to make sure we run this long enough because it is a slow, it's a slow evolution, so we need to run it long enough. And let me see whether I have this parameter set correctly. Just a second. Yeah, we have that already, so we can just start running it. So you saw a slight little move over here, which corresponded to the perturbation. And now you see, well, the amplitude seems to be slightly smaller here than there. But there's not really much happening right now, at least not visibly. But we know it's a slow evolution, so let's see. I guess you can imagine that maybe this dip is getting more pronounced. Maybe. Let's just see what happens. Okay, I think now one can see that this maximum is actually getting smaller. We cannot really see clearly how the wave number changes. I mean, the perturbation calculation tells us in particular that the wave number changes. That's hard to see in a plot like that. But we know the amplitude depends on the wave number, and so if the wave number changes, the amplitude will change, and that's what we see now. So here the amplitude gets smaller and smaller, and the wave number actually gets bigger, so the wavelength gets shorter. And now, now something really qualitatively happened, where one of those wavelengths actually just disappeared. And so we see that the linear evolution was that the perturbation grows, and at some point it becomes very fast, and then we just lost a wavelength. And that means that initially the wavelength was too short and the wave number too large. And after the perturbation kicked in, we removed one wavelength, and so the overall wave number became smaller and the system ended up in the stable regime. So here we see the space-time diagram where very long, it's very hard to see anything. And eventually see how here the amplitude gets smaller and smaller, and this maximum disappears, and you have later only 11 wavelengths in the box rather than 12, and so the wave number became smaller. This process here, where you lose one wavelength, is called a phase slip, and that's a characteristic feature arising from an Eckhaus instability. Okay, so that means that instability seems to bring the system back into the stable regime. Well, we don't quite know. I mean, we would have to run longer to see whether it's now really stable, or we could compare the wave number with the wave number, the stability limit, but let's not do that. Rather, let's explore this long wave feature of the instability, because we said that the Eckhaus instability is a long wave perturbation, is a long wave instability. So if the system was shorter, or if you made a perturbation that has a shorter wavelength, it may actually not grow because there's this fourth order derivative which suppresses the growth if the wave number is too large, the perturbation wave number, that is. So let's try that. Let's first prepare the same state again. So again, we have the same 12 wavelengths in the box. And now we again have to run for a longer time, like T100, 300. And we make a perturbation, and this time we take the same modulation amplitude, but we take 2 periods of that perturbation in the box. So look at, see, this was the perturbation we applied before, and so now we apply this perturbation, and you see now we have shifts here, no shifts here, shifts here, no shifts here, shifts here, no shifts here, and so on. So now we actually have twice as many modulation periods in the box. And let's see whether this now again leads to a phase slip, or does it relax back. So you see the amplitude is slightly suppressed here because of the compression, and similarly here. So we have 2 compression sites, and one has the feeling that actually the amplitude recovers, right? It doesn't go further down. It actually comes, it's now almost constant already. So indeed, as the theory predicted, the perturbation grows when the wavelength is sufficiently large. For shorter wavelengths of the perturbation, the perturbations do not grow. Let me do one more simulations to emphasize another aspect. Well, maybe we don't want to. Well, we have to wait until it's over, otherwise we have to set up the windows again. So the aspect I want to emphasize or illustrate is that we showed in the phase diffusion equation that we derived that diffusion coefficient is depends on the wave number. But we also saw in the simulations that as the perturbation evolves, the wave number, the local wave number changes. In particular, where this dip occurred, you had more and more compression, so the wave number get larger and larger, which means that it got further and further into the unstable regime. And so that's why the growth actually accelerates in the process. So let's just do that once more. We need to do this, and Tmax just 10. So okay, and now we do a perturbation, a small perturbation amplitude, and only 1 wavelength. So we actually have a growing perturbation, and let's do only run to 200 now. And so again, we have to be a little bit patient, but we see the dip here in the amplitude, which we know will grow with time. And what we also should be able to see is that the compression here gets somewhat larger, meaning that the wavelength gets a little bit shorter. But that's not visibly, not really striking, at least not yet. So the amplitude goes down because, remember, the amplitude depends on the wave number, and the wave number, and when you go with the wave number towards the neutral curve, the amplitude goes to 0, right? And so we're now going, the wave number, you see the wavelength is now shorter. The wave number gets larger, gets towards the neutral curve, and at the neutral curve, the amplitude would be 0. So as this wave number here grows, the amplitude goes down, and but also as the wave number grows, the diffusion coefficient becomes more and more negative. And so that's why this process accelerates substantially in this final stage. And within the phase diffusion equation that we wrote down, you would actually have a singularity within in finite time. So let's maybe just have this process go to the end, but we've seen it already. So it's actually, let's maybe just do this. Just for 10, and so right. So now it was very fast. This last part is very fast because the diffusion coefficient is extremely negative. And also, I should say at some point this phase equation breaks down, right? We assumed the wave number changes slowly in space and time. And clearly in this last phase, that was not the case anymore. So this equation is okay until shortly before that phase slip really happens. Okay, but we now have a good feeling what happens with steady patterns. We have a range of stable wave numbers. And when you go outside that range, low or high wave numbers, you get this Eckhouse instability, which brings you back into that stable range.